Let's wait for 2 3 minutes. Then I will start. Okay, let's start. So this is week 6 of the course Mathematical Method in Physics 1 problem solving session. So today we will just continue with the problem of that some kind of a natural physics problem of whatever we have seen the mathematical part of the homogeneous differential equation with order 2 and with constant coefficient. That is what we have seen in the week 5, where we have seen that there are three different kinds of roots which are possible, and corresponding to them, there are different solutions. And for the homogeneous ODEs, we have seen that we have only the complementary solutions. And I have mentioned that for the inhomogeneous case, for the same thing like the second order differential equation, you need these complementary functions. Along with that, you require to calculate the particular integral. So that calculation or computation of particular integral along with the complementary functions, we will try to see in this particular class. Okay, so before going to the inhomogeneous part, let's first discuss uh, an example, an example of homogeneous ODEs of order 2 with constant coefficient. This is what we have seen in the last class. This time we will just discuss about one of the examples of the this kind of a problem. Okay, so we will start with the vibrations in the mechanical system. This is one of the very famous example of this kind of an equation. So let us start with, so suppose consider a spring mass system, which is one of the examples of this mechanical system. So it's a spring mass system, right? And you have what is the spring mass system consists of? A spring, definitely, with spring constant, which is the natural property of the material of the spring. So this is spring constant K with a mass m attached to a nearby wall. Okay, to a nearby wall. Okay, so the system is something like this. Suppose you have a wall here, and this is the floor, and you have a spring with spring constant K, and with that a mass m is attached to it. So this has a spring constant K. Okay, with this you have a mass m attached to it. So suppose this is the position, its original position of the mass. Now what you have to do is that you apply some force on this particular mass so that the spring, now we change the color here. Now the spring now becomes like this, and the new mass, not the new mass, but the same old spring mass system now looks like this. Okay, so now this is the position of the mass which was there in O. Now it is supposed at O dash, and let this distance be some x. Okay, so whatever force we apply here, so that force is observed to be equal to minus k times x. This minus represents the restoring force. So what do you mean by the restoring force? Is that if you apply a force, if you give a force to this mass in this direction, particular which is written here in this direction, as we do it, there is a tendency of the mass and spring system to come back to its original position. That is, the mass tends to come towards the point O, that is its origin or the equilibrium point. Okay, so that restoring force which is developed in this mass m is actually equal to k times x. This is very famously known as the Hooke's law. Okay, so this is what your spring mass system consists of, and this is what your force represents. So how do we write the force? We know that force is nothing but mass into acceleration. And can I write the acceleration as d2x dt2? Yes, we can, because x is the displacement and we are taking the double derivative of the displacement to calculate the acceleration. And that will be equal to minus k times x. We can write further that d2x dt2 is equal to minus k by m times x. And we sometimes write this d2x dt2 is equal to minus omega square x, where omega is equal to root of k by n. So that omega square becomes k by n. Okay, so this is how we can write. All right, this is fine. And further, you can write this as d2x dt2 plus omega square x equals 0. This becomes the ordinary differential equation of order 2, but with constant coefficient because k is also a constant. It's fixed for the spring, and mass m is also a constant, which is fixed in this particular system. So omega square itself is a constant quantity, and hence we have found out a homogeneous because there is nothing over here, it is absolutely zero on the right hand side, no forcing. So we are getting a homogeneous ordinary differential equation of order 2 with constant coefficients. And we know how to calculate or how to find out the solutions. We have already detailed discussion we have done. So we know that the solution for this, so I am just writing, we know that only the complementary function of the complementary solution will be there. So we know that the solution for this ODE will be x because x is the variable, the independent variable. So x of t, sorry, the dependent variable, x which is dependent on t, which is equal to some a cos omega t plus b sin omega t. So you will get actually from here, if you look at the auxiliary equation, which we have seen in the last class, that is, uh, it is actually, you will get the iota roots, like the imaginary roots. And corresponding to imaginary roots, we have seen that we can reduce that to be a cos function as well as the sine function. So this is the solution. And this particular solution represents oscillations. Represents oscillation. So there will be oscillation with, I would say, angular frequency omega. That's all. This is what we generally deduce from the Springmer system, and we know all about the Springmer system, but this is how the differential equation is found out. Now, there is another important case for this particular system. We can now try to do some experiments, and right here, say the second case. Now, consider now, okay, so this is now the case 2. So consider in the same Springmer system, now you consider now that there is a damping force. Okay, there is a damping force due to viscosity of the medium. All right, so this is fine. You have the viscosity of the medium. So now what is happening is that you have the spring mass system and you dip it in some kind of a, say, some viscous medium, viscous fluid, and try to do the same experiment. You try to stretch the spring and leave it, and you will find out that there will be a restoring force which is developed. But once we give the force, there is an opposing force due to the viscosity of the medium. So these are the two things. So viscous medium, you just dip it over the viscous medium. Okay? So what you will get, let us say, let us consider or let us say the damping force which is developed. Damping force is say Fd, which is proportional to the velocity with which the mass will be moving when a force is applied. So what is happening is that you have now the same spring mass system. So here is the wall, and you can see there is a mass which is attached, and you give a force. Now what you happen is that this is a viscous medium. Okay, so once you get a displacement, there will be a damping force which will oppose this particular force which we are applying. Okay, so this is the viscous medium, as you can see, or as we are developing. Okay, this is a viscous medium. So this is how we are trying to look at this particular experiment. So we are saying that the damping force is proportional to the velocity of the movement of the mass of the spring mass system. Okay, not the spring mass system, but the mass. Okay. Now, so FD is equal to some constant of proportionality, let's say L. So L is some damping constant, right? So this is the damping constant. If this is true, then what will be your net force? That is what is the question, right? So the net force which we are applying will be equal to kx with a negative sign, of course, and there will be some L times b. This is what is my new force looks like. So you have a restoring force. The mass will itself will have a restoring force when you give a force. So this is a restoring force from the Hooke's law, and this is again a negative force, which is the damping due to the medium. So this is coming due to the medium. You can write due to the medium and its viscosity, but this is coming only due to the spring's property. All right. So this is the net force. Now force can be written again as what? Mass into acceleration. You can just write it like this. That will be equal to minus kx minus L times d. Correct? So d2x dt2, we can further write this as minus k by m x minus L by m b. All right? We can take it in the left hand side. So d2x dt2 plus, let's say, L by mv I am writing, plus k by m times x equals 0, right? So d2x dt2 plus L by m, v can be written as dx dt plus k by m into x, which is equal to 0. Now look into it. See, L is a constant, right? M is a constant, k is a constant. Of course, m is a constant, we have already said. So again, we have developed. So this is again a homogeneous ODE of order 2 with constant coefficient. So again, the solution will be based on whatever we have discussed in the last class, constant coefficient. Okay, so there are three possibilities we have seen: whether you have real roots with different roots, you have exponential decay or exponential growth like functions. Second is you have exactly equal roots but real. In that case, you have c1 plus c2 t times exponential of something t. This kind of a function will be developed. And finally, when you have imaginary roots, you have your oscillatory system. So oscillatory system, we have already seen that in the first case we have got. Does the same oscillatory system exist here? We will see that. Okay. So how to find out the solution? So for solutions, what we take is the auxiliary equation. What is that? Alpha square. Let this be equal to 2b. We generally write it as 2b. So let me just cut this and write it again. So d2x dt2 plus 2b dx dt plus omega square x equals 0. So what we are writing is that 2b is equal to L by m, omega square is equal to k by m. That's what we are trying to write. Or b is equal to L by 2m. This is how it is defined. So that's all. Fine. Now we try to look for the solutions, right? And for the solutions, it will be only the complementary functions, no particular integrals because it is not inhomogeneous. Fine. So for that, we write the auxiliary equation as alpha square plus 2b alpha plus omega square equals 0. And can we factorize this? Yes. Alpha is equal to minus 2b plus minus root over b square, right? So it will be 4b square minus 4 omega square because a is 1. So this is 1. So it will be 2. So alpha can be further solved minus b plus minus. This 4 can be taken outside as 2. This 2 will be cancelled. It will be b square minus omega square. So this is the final alpha. Then what will be the solution? X of t will be equal to c1 exponential to the power minus b plus root b square minus omega square times t plus c2 e exponential minus b minus root over b square minus omega square times t. Okay, just a minute. No, no. Yeah, this times total times t, right? That is the complementary function solution or solution. Okay, this is the final solution. Great. Now, what we do is that we just write it once again. X of t as e to the power minus bt. I am taking common. So I can write c1 e to the power root over b square minus omega square t plus c2 e to the power minus root over b square minus omega square t. Great. So are we finding out the oscillation here? Well, looking at the expression, we can see that some kind of damping is happening, but with exponential growth and exponential decay. We are not finding any oscillation. But can we generate any oscillation in this particular system? Maybe. Let's see what conditions are required. So let's say we call those as cases of damping. Let's see by putting the different cases. We know that this factor b square minus omega square root will tell us the conditioning of these factors root over b square minus omega square. So I can write it conditioning of root over b square minus omega square will tell us whether there exists any oscillation or not, or there exists any oscillation or not. Right? Because we will get the imaginary roots, and whenever you get exponential imaginary times something, you can deduce it or reduce it into cos or sine. That is what is the main aim. So let's take the first case, which we call as underdamped. Okay, underdamped. The case for underdamped is that your b square is much less than omega square. Okay. In that case, what will happen? Your root of b square minus omega square, since b square is less than omega square, this becomes negative, right? If I would say not this becomes negative, yeah, this becomes negative. If under the root something becomes negative, you get imaginary solution, right? So this is we are getting great. If you are getting imaginary solutions, how will you write it? So x of t will be e to the power minus b of t, and let's say beta is equal to say root over b square minus omega square in this case. So can I write this as c1 e to the power iota beta plus c2 e to the power minus iota beta? And we know this kind of solution can be written as in terms of e cos beta t plus b sin beta t, right? And this represents some kind of an oscillation. So you will definitely get an oscillation if your damping factor B, right? If your damping factor B is much less than omega. If it is there, then you will get oscillation, but with a damping. So this is the damping part. You have damping. That's why it is under damped. You have some damping, e to the power minus beta t. With the time, there will be some damping, but along with that, there will be some kind of an oscillation. So I would say that it will look like something like this. So you have an oscillation, which is start damping like this. Okay, so this is the damping part. So this some kind of this oscillation will be there. So this is the first case where there is an under damping. Fine. The second case is when you are having critically damped oscillation, right? You have critically damped oscillation. So in this case, critically damped, that means what? You want a critical value below which there will be an under damping, above which there will be an extra damping or over damping, we will say. So critical damping means B is equal to omega. This is the case of the critical damping. Okay, so if you put this B is equal to omega and try to see this part, what will happen? See, both this will be equal to e to the power 0, e to the power 0, that means 1, right? So, or if you come here, somewhere here, let's see. So, if B is equal to omega, then your alpha will be equal to minus B, right? So, then your alpha will be equal to minus B, correct? The auxiliary equation. That means what? Roots are real and equal. So in this case, we know that the solution will be x of t, which is equal to t1 plus t2t into e to the power minus bt. All right. So you can clearly see that there is some kind of a damping which is present here with time, but there is linear function as well. Okay. So there is a linear function in time, a straight line in time. Along with that, there will be some kind of a damping. Okay. So this is a kind of a uh, function or a solution for the critically damped. Most important thing is that you have to write that the oscillations are now absent. Below this, if B is just less than omega, then there will be some kind of an oscillation with damping. But here, when you are putting the damping coefficient exactly equal to the natural frequency omega, that is for the spring mass system, if you just equate it with the natural frequency, then the oscillations becomes absent or absent. So in this case, the oscillations are absent. This is the critically damped case. Third one is your over damped case, just above the critically damped. Okay, so this is the over damped. So what is happening in the over damped? We have seen that under damped means B is or the damping factor is less than your natural frequency omega. But in case of over damped, it will be the exactly opposite. B square will be greater than omega square. Okay, or B will be greater than omega. So in that case, it is the original whatever we have found out. We can write it the same way. X of t is equal to a e to the power minus lambda t plus b is e to the power minus some mu t. Why we are writing like this? Because lambda is equal to b plus root over b square minus omega square and mu is equal to b minus root over b square minus omega square. So you can clearly see that if you put the lambda over here, it will be minus b minus root over b square minus omega square. And here in the second term, the mu becomes this. So it will be minus b plus root over b square minus omega. Exactly the same solution what we have discussed here. This one. Exact same thing will be there, but with these kind of equation. Okay. We are just writing the same thing. So here damping is so large that there will be no oscillations. Okay. So what we have seen that only in the case of under damping, we are getting some kind of an oscillation, which is this one. Only in the case of under damping, b square is less than omega square. We are getting some kind of an oscillation with some kind of a damping. Of course, damping will be there. We have introduced damping with the viscous medium. Critically damped, it is that region or that solution below which, if the damping is just below the natural frequency, you get some kind of an oscillation. At that point, you don't get oscillation. After that, you will never get the oscillation. So that is what the three cases which is shown here. So this is the direct example of the physics based on the mathematical part which we have discussed in the last class. Okay. Now let's go to the next part, particularly the contents of the week 6, that is the inhomogeneous ordinary differential equation. So let me write. So it will be inhomogeneous ordinary differential equation of order 2 with constant coefficient. Okay, so this is what your next task will be. That what how will you solve for the inhomogeneous ordinary differential equation? We have seen about the homogeneous one. Now we will look for the inhomogeneous ordinary differential equation and how to solve this. So for inhomogeneous ordinary differential equation, there are two solutions as I have mentioned earlier. So for this, you have both the complementary function, complementary solution also you can write, and there will be some particular integral or particular solution. You can say integral or solution, whatever you want to write. Okay, and this is called the YP. And complementary, we have already seen in case of homogeneous equation, this is YC. So the next solution will be YC plus YP. This is the net solution for the inhomogeneous. Okay, let's take an example of inhomogeneous differential equation. So let's see example. So A2 d2y by dx2 plus A1 dy by dx plus A naught y is equal to f of x. This f of x is some kind of a forcing. Okay, some kind of a forcing factor from function, I would say. All right. So how to find out the complementary solution? So for complementary function or complementary solution, we just put fx equals 0, make it homogeneous. So that means it make it homogeneous and then solve. Right. So in that case, what it will be? So it will be a2 alpha square plus a1 alpha plus a naught equals 0. And in that case, you will find out the alpha. So we have discussed, right? This one we have already discussed. And you write the y is equal to some c e to the power plus minus whatever alpha x. Right. So this is how you try to find out the complementary function. But now in this case, you have some function f of x. For that, we are trying to now go towards the how to find out. So how to find particular solution. This is our main question for today's class, right? And we will try to see another system where we will try to see the physics, how we can apply these mathematics in the physical system. Okay, so to find the particular integral, we have certain steps. So number one is that, say, suppose we have f of x is equal e to the power ax. All right. If you have f of x is equal to e to the power ax, so what you can write is that f of d is equal to e to the power ax. What is this f of d? Is Say suppose let us take an example. Let us say that you have d2y by dx2 plus some c1 dy dx plus c2 is equal to c2y is equal to e to the power x and some such as p naught, whatever. Okay. Can we write this as p naught d2 plus c1 d plus c2 times y is equal to e to the power ax, where d is the differential operator d dx. Okay. We are writing this part as f of d. Okay. And this is the particular solution yp. So f of d yp is equal to e to the power ax. So yp is equal to e to the power ax divided by f of d. So if y of p is equal to e to the power ax divided by f of d, then how to find out? Then there are rules to find yp. So what are those rules? Let's see. So 1 upon f of d e to the power ax can be written as 1 upon f of a e to the power ax. Okay, we can just write yp as 1 upon f of a e to the power ax. So here we just put f of b is equal to a. So where from we are getting a? A is here. So e to the power ax, this a I will put it here and then try to see what is the result. Now, in this case, what will happen if f of a is equal to 0, then what will happen? If it is 0, then it goes to infinity. We don't want an infinite solution, right? We need a convergence of solution. If this is the case, then what will you do? Then you differentiate the denominator with respect to x, and in the numerator you multiply by x e to the power x. So what we are doing is that if this is the case, then multiply x in the numerator and differentiate fd with respect to x and put d is equal to x. That's all. Similarly, now if further if dash of a is also equal to 0, then what will happen? Again, repeat the same step. Repeat the same step. Means it becomes x square e to the power ax divided by f double dash and so on. This will be the rules to find if you have an exponential function on the right hand side as a forcing function. So let us take an example of this. Let us solve a question corresponding to this. Okay, you have d2y by dx2 minus 3 dy dx plus 2y is equal to e to the power 3x. Okay. So you have your f of x as e to the power 3x. Okay, so we will apply the same kind of a step. Okay, fine. So what is your f of d? First of all, it will be d square because it's only differentiation minus 3d plus 2 times y. We want particular solution that is equal to e to the power 3x. Therefore, y of t is equal to e to the power 3x divided by f of d. Now, what is this f of d? Yp is equal to e to the power 3x divided by d square minus 3d plus 2. Alright, this is what you have. Now, your a is equal to 3, right? Because e to the power ax is equal to e to the power 3x. So a is equal to 3. Fine. What I require is f of a. So what is f of a? F of 3. What is that? 3 square minus 3 times 3 plus 2. So 3 square is 9 minus 9 plus 2. So f of a is 2. So f of 3 is equal to 2. Then your y of 3 becomes what? E to the power 3x divided by 2. Alright, so this becomes your yp. So yp becomes e to the power 3x divided by 2. Simple. Now, this is the particular solution. So hence, particular solution is half e to the power 3x. But what about the complementary solution? So let's do the complementary solution. So you have d2y. No, no, here, let me write complementary solution. So what is that? d2y dx2. Again, writing the whole equation. dy dx plus 2y is equal to, put it equal to 0 and do the same auxiliary kind of a problem. Okay, that is equal to 0. Alpha becomes 3 plus minus root over b square means 9 minus 8 divided by 2. Correct. So alpha is equal to 3 plus minus 1 divided by 2, which is equal to 4 divided by 2 means 2 and 1. So your y of c becomes c1 e to the power 2 x plus c2 e to the power x. Okay, and yp already we have found that is half e to the power 3x. Therefore, the next solution y is yc plus yp, which is equal to c1 e to the power 2x plus c2 e to the power 2x plus half e to the power 3x. This is the solution. Okay, so this is how we have to proceed for inhomogeneous differential equation of second order and with constant coefficients. We have to first find out the particular solution or complementary solution by making it homogeneous, and then try to figure out based on the function on the right hand side or the forcing function, we try to see different rules. One rule we have found out, if your fx is e to the power ax, then what you have to do. Okay, fine. Now let's take another example of the same problem, that is if you have your forcing function as some exponential function. So let's take another example question. Okay. Okay. So this time it's a third order differential equation, but you can do it. Okay. So d cube plus 2d square minus d minus 2 y is equal to e to the power x. Okay. So this is third order ODE and inhomogeneous. Okay. So it's easy. We can do this. It's not so difficult. So let's find out the complementary solution. Okay, let's find out the complementary solution. So your y of c, how to find out? We know the procedure. The procedure is that you have to find out the auxiliary equation, which is this, which is equal to 0, and how to how to see whether which problem. So just put let alpha is equal to 2 and see whether it is becoming 0 or not. So it becomes 8 2 cube plus 2 into 4 minus 2 minus 2. Is it fine? Yes. Okay. Let's see what it happens. So 8 plus 8 minus 4, right? Which is not equal to 0. Okay. Let's take alpha is equal to minus 2. So you get minus 8 plus 8 minus 2. Sorry, this will be minus plus 2, this will be minus 2. So this will be 0. Therefore, alpha is equal to minus 2 is one of the solutions. One of the solutions. Correct? This is one of the solutions. Now, if you have got this, can I write alpha plus 2 and put the other things here? This is how you find out the roots of the cubic equation. Correct? So just put it. So, let's yeah, alpha square. So alpha cube plus 2 alpha square. Minus minus, this becomes 0. This becomes minus alpha minus 2. And just minus 1 if you put, this becomes minus alpha minus 2, which is again cross. So alpha square minus 1. So alpha plus 2 into alpha plus 1 into alpha minus 1 equals 0. Therefore, alpha is equal to minus 2 minus 1, 1. Then yc will be what? Simple. C1 e to the power x, C2 e to the power minus x, plus C3 e to the power minus 2x. That's all. This is your complementary solution. Let's look for, now let's find out the particular integral or particular solution. All right, what is the particular solution? Okay, let's write it in terms of f of d, which is nothing but d cube plus 2d square minus d minus 2. All right, so f of d times y of t is equal to e to the power x only. So y of t becomes e to the power x divided by f of d. If y of t is equal to this, we know the set of rules to find out the particular integral or particular solution. How to do that? What is a here? So e to the power ax is equal to e to the power x. So a will be equal to 1. So f of a, which is nothing but f of 1, will be what? 1 plus 2 minus 1 minus 2. 2 cancels out, 1 cancels out. So f of 1 is equal to 0. Now, since y of t is equal to e to the power x upon 0, this is not possible. Then the next step is to multiply x in numerator and differentiate differentiate fd once. Okay, so y of t will be what? Therefore, you multiply x, e to the power x was always there. And what about here? It will be f dash of a. So what is f dash of d? Let's try it. So it will be 3d square 4d minus 1. Correct? Put f dash of 1 again because a is 1. So 3, 1 square plus 4 into 1 minus 1. So it will be 3 plus 4, which is 7, minus 1, which is 3, which is not equal to 0. Therefore, finally, your y of t will be equal to x e to the power x divided by 6. Final solution is therefore y is equal to yc plus yp. Therefore, y is equal to c1 e to the power x, c2 e to the power minus x, c3 e to the power minus 2x. These are complementary solution and plus particular solution x e to the power x by 6. So this is the answer. Fine. This is how you have to do. You have to calculate when the forcing function, that is f of x, on the right hand side in homogeneous ODE, you have the forcing function as e to the power ax, something of the order e to the power ax. Fine. So these are the two examples of when you have the f of x as e to the power x or ax kind of it. Okay. Next is when you have x to the power n kind of it. So we will try to look for one example and try to show you. Unit. Okay, let's go ahead with another f of x. Now let us consider that in the inhomogeneous ODE of second order or third order, whatever it is, you have your f of x as x to the power n. Okay, so something like this. So the second case, you have your f of b times y is equal to x to the power n. If this is the case, then how to find out your yp? So in this case, your y of p can be written as x to the power n upon fd. So the solution is that you do f of d, its inverse times x to the power n. That's all. This is the step you have to follow. Okay, so the rule is this. Okay, let's take an example and try to show you that how you can find out using this. So you have an example d2y by dx2 plus 2 dy dx plus y is equal to x. You can see x to the power 1, so x is fine. The first step is what? Not to find out the particular integral. First is to calculate the complementary function, and for that you need to reduce it to homogeneous equation. So d2y by d. So let's first write complementary solution. All right. So how to do it? This plus 2 dy dx plus y equals 0. Make the auxiliary equation alpha square to alpha plus 1 equals 0. Alpha is minus 2 plus minus root over b square minus 4 divided by 2. Alpha is equal to minus 1. Right? Both the solutions. So roots are real and equal. And what is the solution for that? We already know, we have already discussed. So y of x becomes equal to c1 plus c2x e to the power minus. This is your complementary solution, yc of x. Now to find particular integral. Okay, so for the particular integral, reduce it into some kind of a function of d. So b square plus 2d plus 1 yp is equal to x. So y of p is equal to x divided by some function of d, which is this b square plus 2d plus 1. So this y of p is of the order x upon f of p. All right. See, this one can be written as d square, or f of d is written as d square plus 2d plus 1. Can I write this as d plus 1 whole square? See, this is the same thing. D square plus 2d plus 1. D plus 1 whole square. Can I write therefore y of p x upon d plus 1 whole square? And what is being asked here? Whenever you have this kind of a form, just f of the inverse you have to write, right? So y of p is d plus 1 inverse, like this, times x. This is how you have to solve. Now, what we will do here is that we will approximate. So we will approximate, and we can do it. It's a valid approximation because d is the differential operator. Differential operator. And we know that this differential operator d is much less than 1. So y of p can be written as 1 plus d to the power minus 2 into x. Now expand binomially, what we get is 1 minus 2d times x. So what we are doing to here, from here to here, is that we expand binomial binomially neglecting higher order terms, right? Higher order terms. So you get this. So y of p becomes 1 or means x minus 2 d of x. So y of p x minus 2 d of x means what? d dx of x, which is nothing but what? 1. So y of p becomes x minus. Alright, so this is the solution. Therefore, the net one will be equal to yc plus y of p. Yc we have already found out. C1 plus C2x e to the power minus x plus x minus 2. This is the answer. Fine. So this is how you have to proceed for whenever you have x to the power n or something like that. All right. So now, fine. I think this is okay. Let's go for another set of rules. Mostly you will get questions from this kind of f of x, like either it is e to the power x or it is something else like x or x to the power n. And the next one will be your, yeah, so the next will be about the f of x when it is equal to sine of ax or cos of ax, something like that. Okay. So the third one is that when you have your f of t y is equal to some sine of ax. If this is the kind of a function which is there. Okay. So what happens is that in this case, we have to write it in a different way. Sine of ax, we will write this as f of d square. Okay. We try to reduce with f of d square. Okay. We will see that when we do some examples, you will understand. So if we can write y in terms of sine or cos and fd square, then how we'll solve this? So your y of p will become sine of ax divided by f of minus a square. So f of d square, we have to write it as f of minus a square. Now, again, the same thing happens if your f of d square or which is equal to f of minus a square, it is equal to 0. Then again, you multiply numerator with x and differentiate denominator. But here we have to try to and then try to reduce f of d square again. So we will see. With an example, we will be able to understand. So let us see the question. Say d square plus 4y is equal to cos 2. So I am not writing, so I am not solving here. I am not solving the complete yc. Only we focus on y of p. But remember, the total solution will be always yc plus yp. Okay. So let's see. Y of p is equal to cos 2x divided by f of d square, because there is a d square here. So you can write it as cos 2x upon d square plus 4. Okay. So now what is your a here? 2, right? Because you have cos of 2x. So a is equal to 2. So a square will be equal to 4. D square will be equal to, so yeah, d square will be equal to minus a square. So it will be minus 4. So if this is true, then f of d square, which is equal to f of minus 4, which is equal to d square plus 4, which is nothing but minus 4 plus 4, which is equal to 0. Therefore, f of minus a square is equal to 0. Then in that case, what you have to do? Yp is equal to x cos 2x divided by, now you have to differentiate it. It will be 2d. Correct? Now what you will do is that you multiply it with d, and you multiply, see this x will be there, you multiply d here before the cos. So what you get, y of p will be x d of cos 2x divided by 4d square. Now you put d square is equal to minus 4, that will be fine, and this will be 2 with a minus sign 2x, and this will be 4 into minus 4, which is 50. So it will be 1 by 8 x sine 2x. Okay. So this is how we find out the particular integral. You don't need to multiply this d, or you have to differentiate over this x cos 2x. X will be multiplied in a different way. This differentiation will be only over the sine and the cos. So this is how the yp will be there. Remember, the total solution will be always yc plus yp. Not solved. Okay. But this is we have. So this is another way of solving when you have a sine ax or something else in this particular f of x. Okay, let's take another example of the same thing, and then we'll move to another rules. So there are two more rules which are there through which you can do, and then I will show you another way of calculating the particular solution that you may find easy as compared to this, because these are set of rules which you have to remember, and there will be some confusion which may occur. But yeah, the other rule which I will show, that might, you may feel that will be easy to solve many questions. Okay, and I think that that one becomes much more effective, and I will show that. Okay, so let's take another example for this particular case of sin x or cos x. So you have, suppose an example, d2y dx2 plus 3 dy dx plus 2y is equal to sin 2. Let us solve it completely. So let's check for complementary solution. Okay, so you have alpha square plus 3 alpha plus 2, which is equal to 0. So alpha will be equal to minus 3 plus minus root over 9 minus 4 to the 8, correct? Divided by 2. It will be minus 3 plus minus 1 divided by 2, which gives you either minus 2 or minus 1. So your yc becomes c1 e to the power minus x plus c2 e to the power minus 2. So we have found out the complementary solution. Now, particular solution. We have rules, we know. So we try to write it like that. So y of p is sine of 2x divided by d square minus 3d, oh sorry, plus 3d plus 2. I think this is right. Yes. Okay, so you already have a d square. So you can write it, correct? Okay. So what we'll do is that this is not the function of d square. Remember, you have a d square, no doubt, but I would say that this is okay. Let's put d square is equal to minus a square, right? D square is equal to minus a square. And what is that? Minus 2 square, which is minus 4. Can you put it here? Yes, we can do that. So we get sine 2x divided by minus 4 plus 3d plus 2. So we get sine 2x divided by 3d minus 2. Is it fine? Yes. Now, again we have to, in some way, because since there is a d again here, we have to some way make the denominator in terms of d square. Because this rule is particularly for d square, as you have seen. So sine 2x, let us multiply here 3d plus 2 and divide by 3d plus 2 again. And here it is already there 3d minus 2. Correct? So yp 3d plus 2 you can put it here. Sine of 2x will be here. And you have a plus b into a minus b. So it is 9d square minus d square is there. You can put d square is equal to minus 4. So y of p is equal to 3d plus 2 into sine 2x. D square is minus 4. 9 4s are 36 minus 4. So y of p becomes minus 1 by 40 3d sine 2x plus 2 sine 2x. Correct? This is how you can write. So y of p becomes minus 1 by 40. Now differentiate sine 2x. So it becomes 3 times 2 cos 2x plus 2 sine 2x. Alright? And you can take 2 outside. So it becomes minus 1 by 20, 3 cos 2x plus sine 2x. This is your particular solution. Therefore, y, the total solution, will be yc plus yp always. So y is equal to c1 e to the power minus x plus c2 e to the power minus 2x minus 1 by 20, 3 cos 2x plus sine 2x. Okay, so this is your another example of when you have a sine x or a cos x as your reference. All right, fine. Next is, let's take two more rules and solve two solutions or two questions, and then we will move towards a, I would say, a physical problem, and then we will move towards another way, that is the way of superposition principle of the solutions to find out the particular solution. That will be much more easier way, I would say. So we will solve two questions based on that, and we will finish today. But before that, let's take two other rules. Okay, so we have looked at uh, this is the third rule, I think. Yes. Okay, the fourth one is when you have some ODE in terms of this 1 upon FD, some function of this differentials e to the power ax, some function phi. It can be any function. Okay? So let's take a question, or let me show you that how you can find out your y of p in this case. It will be e to the power ax. Phi of x will be multiplied simply, and this will be f of a plus d or d plus a, whatever you want it to be. Okay, so this is how the particular solution needs to be found out. So suppose you have a question, find the particular solution solution of d square plus 6d plus 9 y is equal to e to the power minus 3x divided by x cube. So here phi of x is nothing but 1 upon x cube and e to the power minus x is already there. So your y of p e to the power minus 3x 1 by x cube as it is will be there, and this will be d square plus 6d plus 9. Clear? Now what you have to do, you calculate f of b plus a. So here it will be f of d minus a. Correct? Just replace f of d with f of d minus a. So your y of p e to the power minus 3x divided by x cube divided by this part will be d minus 3 whole square plus 6 of d minus 3 plus 9. Right? This is the rule, and this is what we are proceeding with. Minus 3x by x cube as it is. And here what you will get, d square plus 9 minus 6d plus 6d minus 18 plus 9. So 6d will cancel, 9, 9, 18 will cancel. So you have only d square. So y of p e to the power minus 3x 1 by x cube divided by d square. So what will you do now? Just take it out just above b minus 2 e to the power minus 3x and divided by x cube. Alright, so what will happen is that, see, this e to the power minus 3x, this d minus 2 will be only above this f of x, okay? So e to the power minus 3x, so it will be d minus 2 of 1 upon x cube. That's all. That's all what you have to do. Okay, so this becomes e to the power minus 3x. This will be what? 1 upon 2x. If you do it 2 times, if you integrate, you get this. Alright, so this is the way to find a particular solution. Remember, this the differential will be on the phi of x. In this case, which is 1 upon. Done. This is rule number 4. And finally, the rule number 5, which is much more trickier, I would say. So let's finish this with one example, and then we will go towards the resonance or force vibration kind of a system. Okay, of a harmonic oscillator, and then we will look for another way of solving the inhomogeneous differential equation. Okay, just a minute. Okay, so the next one is, if you have something like this, x to the power n sine of ax, if you have this, you will get the solution as the imaginary part of e to the power iota ax 1 upon f of d plus iota a x to the power n. This is the solution. Now, if you have 1 upon f d x to the power n cos of ax, then it will be the real part of the same e to the power iota ax 1 upon f of b minus iota. Just remember this x to the power. Clear? This is how you have to proceed. Okay, let's pick a question and find out. So this is the question: d square minus 2d plus 1 y is equal to x sine x. Okay, this is of the form x to the power n sine ax. So a is equal to 1. Okay, so how to do it? F of d plus, because it is a sine x, d plus iota a has to be made. So let's check that d plus iota a. How do we write it? It is d plus iota because a is 1, correct? So d plus iota whole square minus 2d plus I plus 1. This should be the f of d plus iota. So let's do that. D square iota square will be minus 1, 2 iota d minus 2d minus 2I plus 1. Okay. So minus 1 plus 1 goes d square, okay, minus 2 minus I. I'm sorry, 2 can be taken out. 1 minus I d minus 2I. Right? This we are taking. Minus I have already taken out, right? So this is fine. All right. Therefore, so how to find out the particular solution is simple. Y of p will be equal to the imaginary component of e to the power iota x 1 upon f of d plus iota a. So which is, we have already found out, d square minus 2 1 minus I minus 2I. Correct? This times x, because x to the power n was there, so it is now here x. Fine. Let's go ahead. Yp, imaginary root or imaginary solution of e to the power iota x. Now what I do is that 2 iota I will take common with minus sign. Okay? And one x is also there, where it's fine. Okay, so if we can write it like this. So 1 minus 1 plus iota d minus 1 upon 2 iota d square. This is how we can write, but we can inverse times x. Okay, so this is how we can write. So y of t is the imaginary component of, okay, this is like this. What we can write about e to the power iota x is cos x plus iota sin x. What about this? Minus 1 upon 2 iota can be written as iota by 2 with a plus sign. And in between this, we can write 1. See, d square is the differential, which is very small quantity. So d square can be neglected. It is very, very small. Okay. So we only have these terms, and we will do a binomial expansion. So it becomes 1 plus iota times d times a. Okay. So what we have done here is that binomially expanded, binomially expanded and neglected higher order terms. Right? Also, we assume d square is tending to 0. Fine. So the next step will be y of t, which is nothing but 10, imaginary part of, let's write it, cos x plus iota sin x, right? With iota by 2, of course. and you have 1 plus, again I'm writing it for the d times x. Fine. Let's go to the next step now. Same imaginary part of. So it will be now iota cos x by 2, iota into iota minus sin x by 2, right? Into same 1 plus I d x. Let's go further. Now it will be this multiplied by 1 and this multiplied by this. So it will be iota. This x is multiplied with 1. So let me just write it one step further. It will be easier for everyone. The sin x by 2. And this will be now x plus 1 plus iota d of x. Now what is this d of x? Differential of x, d dx of x, which is 1. Correct? So d of x is nothing but d dx of x, which is equal to 1. Fine. So let's write the next step, which is imaginary part of same iota cos x by 2 minus sin x by 2 into x plus 1 plus iota. That's all. So we can write this further as imaginary part of iota x cos x by 2 minus x sin x by 2 plus iota cos x by 2, this multiplying by with 1, minus sin x by 2, and finally iota square will be minus cos x by 2 and minus iota sin x by 2. Okay, so many terms, but we need only the imaginary part. So it will be x cos x by 2 plus cos x by 2 minus sin x. This is the particular solution. Okay, so we have seen this is the rule number 5, that is to find out the particular integral or particular solution. 1 upon f of d x to the power n sin ax, or 1 upon f of d x to the power n cos a. If this kind of a particular integral if you have, then this is how you have to proceed, and then finally reduce to the solution. So since we have sin x kind of a thing in this particular expression, we are using the imaginary part. If it is cos, then we would have taken the real part, and instead of d plus iota x, we would have taken d minus iota. That's all. These are the differences. Fine. So this is how we go towards the actual solution. So we have already discussed 5 rules to find out particular integral, and we will now apply it in the physical system. So let's do that quickly. So the physical part is that forced vibrations. Okay, forced vibrations. So let us consider a differential equation. Of course, it will be an ODE. So differential equation of a damped harmonic oscillator. In case of homogeneous equation, we have seen a spring mass system. Here we are considering a damped harmonic oscillator, which has the equation as d2x dt2 plus 2b dx dt plus omega square x. This we have already discussed. If it is equal to 0, we have already discussed in the beginning of the class. But now it is f times cos omega t, or omega not t better to write. Okay, this is the forcing frequency. Okay, this is the forcing frequency. So if this is the kind of a mathematical equation, then how to solve it? We have already seen the way to solve. First is to find out the complementary solution. So complementary solution is what? You have to write d2x dt2 plus 2b dx dt plus omega square x, put that equal to 0. Make it homogeneous and then write the auxiliary equation. So how to do that? We assume that y is equal to some e to the power ax or alpha x and then try to put it in this particular solution. So it will be alpha square plus 2b alpha plus omega square into y is equal to 0. Or we can write alpha square plus 2b alpha plus omega square equal to 0 because we want not trivial solutions. So alpha will be equal to minus 2b plus minus root over b square, which is 4b square minus 4ac. So this becomes this divided by 2. So alpha becomes minus b plus minus root over b square minus omega square divided by nothing. So this is the alpha because 2 will be cancelled out. So your complementary solution yc will be written as e to the power minus b and you have for the c1 e to the power root over b square minus omega square t plus c2 e to the power minus root over b square minus omega square t. Right? We have seen several cases in case of the homogeneous equation complementary function. One is the overdamped case, underdamped case, and a critically damped case for this one. But when you have a forcing frequency, forced oscillation, you tend to go towards the concept of resonance. So we need to find out here the particular solution. Okay, particular solution. Now to find out the particular solution, how to do it? So you already have d square plus 2bd plus omega square y is equal to f cos omega naught t. Alright, this is what you have. I'm writing d2 by dt2, this part as d square. Okay, and in the same way, d dt as d. So this is what you have. So for the particular solution, how to write? Simple. This is f is a constant quantity cos omega naught t divided by d square plus 2bd plus omega square. And how to solve it? We have seen that how to solve it. The rule is the rule is to go to this one particular solution of when you have sin x or cos x. We have solved it. This is how you go, right? You try to reduce it in terms of f of d square. Put d square is equal to minus a square. A is this sine of ax. From here, if it go come sine or cos, whatever it is. Put that. If it is 0, then multiply by x and try to differentiate it once again. Let's see how to apply it here. Okay. So this is what you have. The first thing is that what is A? Anything which is with the time component or t component in the cost. So this is omega naught. So A is omega naught. So A square will be what? Omega naught square. Fine. What we need to do is that f of b square will have to be written as f of minus omega naught square. Okay. So y of t becomes, or better to write f of d square becomes f of minus omega naught square, which is equal to minus omega naught square plus 2bd plus omega. So f of d square becomes omega square minus omega naught square plus 2bd. Okay. So now your x of p, instead of writing y, let's say x, that will be better because this is in terms of x. So let me write it in x term, so e to the power alpha t. They let me write this also as x of t, and let me write this also x x of p, particularly is the solution. Okay, so x of p becomes f of cos of omega naught t divided by omega square minus omega naught square plus 2b d. But in any case, we need a d square in the denominator. That is how we should proceed. So for that, what I do is that cos omega naught t, let it be like here, and let me write the thing in the denominator as it is, and then we multiply this with 2bd plus, oh sorry, minus omega square minus omega naught square, and divide by the same thing, 2bd minus omega square minus omega naught square. That's all. So x of t will be f of cos omega naught t. So it will be 2bd minus omega square minus omega naught square. It is mathematical, but I want to show that how it is, how the rules which we have seen is actually followed here. So it will be now 4b square d square. You can see that it is a plus b, a minus b kind of a thing. Omega square minus omega naught square square. Right? This is the expression. Solve it further, it will be somewhat complicated, but better to see. So minus 2b f omega naught sin omega naught t and minus omega square minus omega naught square f cos omega naught t in the numerator. In the denominator, you have things which are already being very well fixed. Okay, so this is how you can write. A negative sign will come because I have made it in such a way that it will be coming. Okay, when you solve, you will get it. So it will be omega square minus omega naught square f cos omega naught t plus 2b omega naught f sin omega naught t. Just rearrange in certain terms, that's all. And this becomes omega square minus omega naught square whole square plus 4b square omega naught. So, right. How did this happen? Because d square we are replacing with minus omega naught square. So it will be getting like that. Okay. So this is how it will be. I'm sorry, this will be I think minus. Yeah. Then this minus d square becomes omega naught square. Right. Okay. So finally we are getting this. Now can we write this xp as f divided by root over omega square minus omega naught square whole square plus 4b square omega naught square? We can write, I'll show you, and there will be a cos omega naught t plus phi, and phi, or I would try to say tan phi, is equal to 2b omega naught divided by omega square minus omega square. This is how we define. Now, how is it happening? Let me show you. Take a right angle triangle. So it is actually coming from the trigonometry. This is phi. Let this be 2b omega naught. This is the definition. Perpendicular upon base is your tan phi. So omega square minus omega naught square. Correct? If you do this, your hypotenuse becomes 4b square omega naught square plus omega square minus omega naught square whole square. Correct? And then your cos of, I would say, okay, we have written it cos of omega naught t plus phi, right? So can I write this as omega naught t plus phi as, I'm sorry, this will be, I think, minus 1. So cos of omega naught t, cos of phi plus sine of omega naught t, sine of, right? So cos of omega naught t will be as it is cos phi based upon hypotenuse. So it will be omega square minus omega naught square divided by hypotenuse, which is root over omega naught square minus sorry, just a minute, omega square minus omega naught square plus 4b square omega naught square plus there will be sine omega naught t and sine phi will be perpendicular upon hypotenuse. So it will be 2b omega naught divided by root over same omega square minus omega naught square plus 4b square omega naught square. Correct? Now, if you look at this expression quite clearly, you will find out that the omega square minus omega naught square cos omega naught t divided by this part. Right? Are you getting this? Yes. Okay. You are not getting the root here because I have defined a root already here. So now this, if you multiply by this, it will be the same as this expression. Okay. Similarly, 2b omega naught upon this. See, you have sine omega naught t, 2b omega naught upon this. So you can write it like this, xp as this. Okay. So it will be exactly the same thing. Fine. And fine. People write the amplitude f of a, which is well discussed in the week 6 content. You can go through that. F square divided by omega square minus omega naught square whole square plus 4b square omega naught square. This is your amplitude, which people tend to write. And there is a resonance frequency. To calculate that, we generally do dfa by d omega naught and put that equal to 0. So if omega square minus omega naught square into omega naught becomes 2b square omega naught. If you do this, you will get this. So either omega naught equal to 0 or omega square minus omega naught square becomes equal to 2b square omega naught. Or sorry, 2b square only. Because omega naught will cancel. So or, right? These two. See, this does not have any meaning because if omega naught is 0, there is no meaning of a constant function. So it has no meaning of a cosine amplitude. So we will stick to this and try to write omega naught as omega square minus 2b square. Okay. And we generally write this omega naught as the omega resonance frequency. Okay. So this is the resonance frequency which we generally write. So this is the one of the physical systems. What I try to show is that not the physics behind that, but the way we have calculated the rules which we have followed to calculate if you have a forcing function as sine ax is the same thing is applied here. Is it correct or not? We see that yes, the approach is absolutely correct, and we can solve and come to the actual resonance frequency. For further details, you can go to the Week 6 content and try to look on your own. Okay, so a detailed solution, mathematical solution, can be found out in this particular notes. Okay, which is not shown, I think, in the Week 6 content. Now, the last part of the today's lecture is that another way to solve the particular solution for the particular solution. Okay. So as we know that for the inhomogeneous equation, we need complementary solution as well as particular solution. Complementary solution already shown in the last class, also today. But particular solution, there are 5 rules which I have shown. If you don't want to follow those 5 rules, this is another easy method to find out. And that method is the principle of superposition. The principle of superposition. Using this, it becomes easy to calculate certain uh, functions like forcing functions. So what does it say is that to find particular solution, we look for linear combination of the particular solution of each of the forcing terms. Okay. So what does that mean? I'll show you. So suppose you have an example. We will solve this in detail. Dx2 plus dy dx minus 2y is equal to, let the forcing function be like this, e to the power x plus x square minus x. Okay. If this is the thing, what we will do is that we will solve for the particular solution of yp1 and let's say this together as yp2. Okay. Then the particular solution, actual particular solution will be yp1 plus yp2. So what we will do is that we individually calculate for the particular integral or solution for this and for this, and then add it. That becomes the particular solution. Now let us see how we can implement this to actually calculate the particular integral. So I have two questions for this part, and let's see whether we how to find out the particular solution. Okay. So I'm sticking to the particular solution and not calculating the complementary function. Complementary function, it is easy to calculate. I'm not calculating it. We are just focused on the particular solution. Okay. So let's take this example only and try to proceed. So the question is that find particular solution for the following ODE, which is d2y by dx2 plus dy dx minus 2y is equal to e to the power x plus x square minus. Okay. Let's consider y1 is equal to b e to the power x. Okay. And let's say y2 is equal to ax square plus cx plus d. Why am I writing it? On the right hand side, the forcing function f of x, here you have one exponential function. This is unique. X square minus x is the polynomial function. This is another unique function compared to the exponential function. So let's take yp1. This is the first particular integral, and this is yp2. Okay. Let us say that let b e to the power x is one of the particular integral solution. Assume. Okay. Let this be the solution. Okay. And let yp2 ax squared plus cx plus b be the solution. And we try to find out the coefficients a, b, and c and d. Right. So what to do is that if this is the solution, if let us assume these two are solutions for the ODE. Okay. Now, if this is true, if the above statement is true, that b e to the power x is the solution of this particular ODE, then we can put it in this particular equation. If you put it, then what will happen? It will be b e to the power x, because e to the power x will be differentiated twice, which will be e to the power x plus b e to the power x again minus 2b e to the power x. And here you have e to the power x. For the time being, we will only take e to the power x. Also, you can take other. That's fine. Okay. So on the right hand side, you can see that b plus b is 2b minus 2b, which is 0. So you are getting 0 e to the power x as e to the power x plus x squared minus x, which is some kind of an invalid. Okay. So now what we will do is that if this is the kind of a case where you are getting left hand side as 0 and right hand side you are getting 1 e to the power x, then we multiply your yp1 as b x to the power x. So multiply by it and try to solve it once again. Okay. So once you do that, your yp1 is now bx e to the power x. Put it in the ODE. So what will happen? So it will be, so let's see, dy with yp1 by dx is, b can be taken outside because the constant. So e to the power x plus x e to the power x. Correct? dyp1 by, sorry, d2yp1 by dx2 will be what? B again. So e to the power x is e to the power x. This will be e to the power x plus x e to the power x. Right? Differentiating this once again. So you are getting b 2 e to the power x plus x e to the power x. Fine. So if you now put it in the equation, then what will happen? It will be 2b e to the power x plus bx e to the power x plus, right? B e to the power x dy1 by dx plus bx e to the power x. Now finally, what is that? Minus 2y. So minus 2bx e to the power, which is equal to e to the power x plus x square minus. So only e to the power x has to be considered because there is no x square minus x on the left hand side. Okay, so 2b, b3b, that's all. So 3b is equal to 1, right? Just check the coefficients of e to the power x. So 3b is equal to 1, so b is equal to 1 by 3. Therefore, your yp1 is equal to 1/3 x e to the power x. This is your yp1. Great. What about yp2? So we have considered yp2 as ax square plus bx plus c. Sorry, not bx, px plus d. So just put it. So d yp2 by dx will be equal to 2ax plus c. dyp2 by dx2 will be equal to 2. All right, just put it in the equation. So it will be 2a plus 2ax plus c minus 2ax square plus cx plus d, which is equal to e to the power x plus x square minus x. Fine, let's go ahead. 2ax plus c minus 2ax square minus 2cx minus 2d is equal to e to the power x square minus x. Check the coefficients of x square, which is this one only. So minus 2a is equal to 1, a is equal to minus half. All right, a is minus half. Great. What about the terms consisting of x, 2a, to c? So it is 2a minus 2c is equal to minus 1. So it will be c minus a is equal to 1. C minus or plus half is equal to 1. So C will be also equal to half. Right. Oh, I'm sorry. Something I'm doing wrong maybe. Uh, yeah, I think it's fine. I think it's fine. Okay. Let's see another one. So the constant part is 0. So 2a, c and minus 2b is there. So it will be 2a. Okay. So it's 2a plus c minus 2d is equal to 0, I think. So it will be 2 into minus half, which is minus 1. This is half minus 2d is equal to 0. So this will be minus half. right? Minus 2d, which is equal to 0. 2d can be go on that side, and this will be minus half. So d will be something about minus 1 by 4. Know whether I have made it correctly or not. Just a minute. Yeah, looks correct only. Okay, fine. So I think I'm getting something like this, but I don't know whether this is the solution or not. So finally, we are getting minus half x square for sure. And actually, the x term will be 0. In some way, I'm doing something wrong. It has to be minus half some way. I have to look into this part. Fine. So final solution will be y of p1 plus y of p2, which is nothing but 1/3 x to the power x minus half x square minus half. This should be the proper answer. In some way, I don't know whether I have made the mistake. I have to see that. Okay, let's do the last question and finish it. I will try to see this one, and in the next class, maybe I can return here. So another question is this: d squared minus 4d plus 3y is equal to x cubed. So what I will do is that yp, since there is only one term, it's a polynomial function, we can write this easily: bx squared plus cx plus d. Don't confuse this d with this. Okay, this is the actual constant coefficient. So yp dash will be pax square plus 2bx plus t. Yp double dash is 6ax plus 2b, and just put it into the main equation. You get 6ax plus 2b minus 12ax square minus 8bx minus 4c plus 3ax cube plus 3bx square plus 3c x plus 3b is equal to xd. So if you check each and every term, you get 3a is equal to 1. Okay, where this is the term 3a is equal to 1. So a becomes equal to 1 by 3. Okay, and further, if you look at, you get something like this: minus 12a plus 3b is equal to 0, which gives you b is equal to 4 by 3. So this is actually coming from here, x square term, right? Next is, once you do this, you get 8b minus 3c, I think is equal to 2 in some sense. So finally, we get c is equal to something like 26 by 9, and d is 80 by 27. These are the four values you will get. So finally, your solution yp will be equal to simple. So a is your, just a minute, let me just write it. So it will be 1/3 x cube plus 4/3 x square plus 26 by 9 x plus 80 by 27. This should be the answer. Okay, so it's one of the easier way to calculate the particular integral. You can try this one out. I think I have done some mistake, or maybe somewhere some problem is there, but at least this part is correct. Something here I am doing wrong. Let me, I will also check. Okay, so fine. These are the ways to calculate the particular solutions. I have discussed in details, and yeah, that's all. So in homogeneous ODEs, we know how to calculate the complementary and particular solutions. That is the main motive of week 5 and week 6. We have covered that today. Okay, so the notes will be available, and if any questions are there, you can ask right now or next week. Okay, so with this, I think I can end. Fine. Okay. If there are no questions, then we can stop today. Thank you.